So in the last few classes, we have been studying about the vectors. So continuing further with the vectors. See, in the last class, we studied about the dot product and its applications. And now we proceed further with the further details into the various applications and the various operations that we do, so that we are able to get some fruitful information when we apply these mathematical concepts of vectors in the machine learning. So here you see that we are computing the angle between the two vectors, and using this formula of cos theta is equal to, in the last class also we discussed cos theta is equal to a dot b, and then we have the magnitude of dot product of the magnitude of the two vectors. So when we are given two non-zero vectors like v is equal to ab and u is equal to cd, then what is the condition when we are going to say that these two vectors are orthogonal vectors? So the condition if their dot product is 0. So the dot product of two vectors u and v, if it is equal to 0, then in that case, what will be the angle between these two vectors? So there is a relationship between that, and this angle information helps us in working with the various machine learning applications. So when we say what will be the angle when the dot product of the two vectors is 0, so that means the cos theta is equal to 0. And when cos theta is equal to 0, when theta is equal to 90 degree. And in that condition, we say vectors v and u are perpendicular to each other. So that means when we are working in both the directions, so if we say you can say if you have an information that cos theta is equal to 90, that you can imply that both the vectors are perpendicular to each other. And if you have the dot product information, from that also you can derive the value of the angle, and then you can conclude that these two vectors are orthogonal to each other, or they are perpendicular to each other. Now what information this if the two vectors your v and u are perpendicular to each other, then what kind of information we derive, right? So let us say you can say v is a one vector that represents one image x, and u vector represents another image y. So what kind of relationship will be there between these two images when we are working on a problem of image classification, let us say? So anyone you can answer this? Simple. So you were right, Arpit, but when we have to tell that thing, like you can say in the non-technical words, then we say these two images are not related with each other. So that means if we have to find out the similarity between the two images, then we are computing the angle cos theta between them. If the angle is less, that means they are coming close to each other, that means they are more similar to each other. So if the angle is going higher side, like it is 90, 180, that means their two images are far apart from each other. So they are less similar with each other, or you can say they are dissimilar with each other. So this is how we are deriving the information between the two images, using the you can say the angles and the using the angles and the dot product of the vectors. So the dot product of the vectors you compute, and then if we give you some example and we ask you, you compute whether two vectors are orthogonal to each other or not. So you just take out your notebook and just compute, find out the angle between these vectors and tell me the answers, all of you. Now when we talk about the vector space, your vector space, it is a set of all linear combination of all its elements. So if we say x and y are the two vectors, then x plus y is the vector space for that particular vector. And if x is a single vector, then we say when we multiply it with a scalar, again we get a vector, and that lies in that particular vector space. So, and when we say that, you can say when we say what is the linear combination, if you have to define, we say that V is a linear combination of the various vectors v1, v2 up to vn if there exist scalars x1, x2 such that v is equal to x1 into v1. So that means when we multiply any vector with the scalar, then we are after that we are computing the combination of that. Then we say that you see this example, when we multiply two multiply a vector 1 by 1 2 with the 2, and we take another vector and multiply it by 3. So 2 and 3 are any of the scalar variables. You can say they are the scalars with which we, scalar constants basically, with which we are multiplying these values of the vectors. Then we say the addition of these two is a linear combination of the vector 1, 2 and 3, 4. So this is the sake for your information, so that you can understand how do we define the linear combination of the vectors. And geometrically, you can say the linear combinations of a non-zero vector, it forms a line. And when we have the linear combinations of two, see, when we have a single a vector, at linear combination of a non-zero vector, it will form a line. And when linear combination of two non-zero vectors, we will be having, they will be forming a plane, unless they are, both of them are not collinear to each other. So if they are collinear, definitely it will be a line. But if they are not collinear to each other, then they will be forming a plane. Then when we talk about these vectors, the important thing, see, these projections, they are very important for understanding, because these projections are applied everywhere in the machine learning. So the projection of, you can say, we say the orthogonal projection of a vector v onto vector u. It gives the component vector projection of u over v over u, and it is in the direction of u. So here we have, you can see, we have two vectors, one is vector u and one is vector v, and this v is the, in the diagram you can see the projection of vector u v on vector u. This is how we write. So this is equivalent to the dot product of the two vectors divided by the you can say the dot product of the magnitude of the two vectors into the vector u. So this is the dot product of projection of vector, orthogonal projection of vector v onto to vector u. So if we have to find the orthogonal projection of vector v onto u, then how do we compute that? Just simply understand. So here we have taken the formula, the same formula. So what we are doing? We are taking the dot product of the two vectors, minus 1 into 1 plus 3 into minus 1. So this is the correspondingly, we are multiplying the elements of the two vectors, the corresponding multiplication, u minus 1 into 1, 3 into minus 1, this comes in the numerator. And in the denominator, we see if this is the Euclidean distance, we compute, or the norms, we can say we have taken, that is used to compute the magnitude of the vector. So then we are multiplying it with the vector u. So when we compute this, we are getting some value that gives another vector that represents the projection of one vector over the other. So similarly, when we have to do, see, this is the projection of orthogonal projection of vector v onto u, and if you have to do the reverse, right? So can you do the reverse of that? Now you compute the orthogonal projection of vector u onto v. Then what is the value? So from here we can understand, see, the projection determines the direction, basically in what direction we are doing, and on the basis of that, see, the projection of one vector over the other is not same, right? So that is going to give us the different values. And then that means if it is a new, you can say new vector means new magnitude and the new direction, right? And see, these orthogonal projections, they are being used, you can say, in the various machine learning algorithms, like unsupervised machine learning algorithm, that is principal component analysis. So this principal component analysis, this particular, this is part of your syllabi also, we'll be doing it later. But I'm trying to make you understand the concept, because principal component analysis is used for the dimension reduction. So like when we have, let's say here we are working in the two dimensions. See, when we are talking about two dimensions, there are two elements in you can say, if we take the example of the same flower data sets, we had four features, or you can say we had four dimensions of sepal length, sepal width, petal length and petal width. So these are the four dimensions. Because representing these four dimensions is quite difficult, so I've taken the example of the two dimensions. Now the question is, now we want to project, see, when we have to reduce the dimensions That means we are trying to project the same information from 2D to 1D, right? From two-dimensional space to one-dimensional space. Then in what direction, how this production, like whether we should project x1 on the x2 space or x2 on the x1 vector, or we have to do that projection in some new direction, so that we are not able to lose the information and we are able to reduce the dimension and not compromise with the accuracy of the results, whether we are working with the clustering or whether we are working with the classification algorithms. So we don't want to compromise with the, so we have to reduce the number of dimensions without compromising with the accuracy of that particular application. So here we see these are certain points, and these are the, this is the two-dimensional you can say plane. Now we want to reduce this data into one dimension. Let's say I want to project these data points on a line. So let us say the simple line that we can see that can be drawn is this. Now here you can see I have drawn certain lines. There are certain arrows you can see which are depicting how far these points are. The existing this plus symbols which are there, these are the data points. How far these data points are, they are away from this particular line. So this length of this each arrow, this reflects the projection error. So if that means when we will project these data points on a single plane, you can say in one dimension, in that case on a particular line, that means we are going to get this much of error. So now the task of the algorithm that becomes is how to reduce this projection error. So you can say it's we tried, so we identify those components, or you can say we retain those components in the data set which provide us minimum projection error. So you can say, so if we take, let us say take another example. Let us say if you draw this particular line. So when we draw this particular line, now see the distance of these data points from the this particular red line. So from this line you can see the difference. So because these lines they depict these arrows, basically they depict the projection error. So when we will be projecting these data points on this red line, you will be getting more projection error as compared to the error that we get when we project these data points on the blue line. So this is how we see when we are doing these projections, as we have discussed. So when we are doing these orthogonal projections in the real world exam problems, in that case we are trying to find out that if we project one vector over the other, in that case what is the projection error we are getting, and on the basis of the we take up only those projections will help us in reducing these projection errors. So I hope this example is clear. Anyone having any doubt, you can ask. Yes. So we'll be studying in detail in the PCA, because here we were using the projections. So for projecting the reducing the dimensions from you can say 3D or 4D. So from higher dimensional space to low dimensional space, whenever to do the dimension reduction process, we have to project the higher dimensional data into the lower dimensional data. And this projection process, we have certain projection errors which we want to reduce and find out those components which help us in reducing the projection errors. So reducing from 2D to one dimension, we find a direction of a vector u, so onto which to project the data so as to minimize the projection error. This is the, you can say, the objective of this algorithm, that is principal component analysis, which is meant for the dimension reduction. Now let us say, let us take another example where we are talking about the vector space. So in the vector space, we talk about, see, you can say where these vector spaces are used in the real term. So when we talk about the search engines, you have been using Google, Yahoo, so many search engines you use in order to find the relevant document from that particular search engine. Now how these search engines they are working, so there again we are working with the vector spaces. Now consider the database. Let us take one example and try to understand the concept of vector space when we are working with the search engines. So there we have in the search engines, we call as the vector space as the vector space model, because we are using the geometrical representations of the vectors for this particular model. So let us assume that we have a database of articles from a magazine called Sports, and we, for the sake of simplicity, in order to understand the problem, we have taken just 3 documents. So we have 3 documents, and you can say, and we have only three keywords. So each document can be distinguished on the basis of these 3 keywords. Like one article we have, that is the document 1, it talks only about the cricket. Now we have another document that discusses only about the hockey. Then we have another document 3, which is having 30% about the tennis or 70% of the about the hockey. So that means when we are talking about this is giving the information, the one document is giving the information about the cricket, another is giving about the hockey. So that means most of the terms that in that article, they are related to the cricket. In the second document, most of the terms in that article are related to the hockey. In the third one, it is giving the information about the tennis and the hockey. So more of the hockey and less of the tennis. So now, how can you tell me now how to use the vectors to describe this vector space search engine process of the query sports database? Any one of you? How to represent the vector, this information in the form of vectors?
When we can assign vector directions to cricket, hockey, and tennis.
Now you tell me, like mathematically, what will be a vector over here? How many vectors are there? Let us say
3.
3. Okay. What will be the first vector?
Cricket.
Okay. So what will be there in the cricket?
Percentage of cricket.
Percentage of information. Okay. Anyone else? Anyone else?
Ma'am, we can have 3 dimensions: cricket, hockey, and tennis, and then represent like first document as only cricket. So मैम वो खाली क्रिकेट की डायरेक्शन में होगा,
Hmm.
सेकेंड हॉकी की डायरेक्शन में होगा, और
Hmm.
थर्ड वाले का जो 30% है, मतलब वो टेनिस की डायरेक्शन में होगा और 70% हॉकी की डायरेक्शन में होगा, उन दोनों
हाँ,
के
तो
बीच।
उसको उसको वेक्टर फॉर्म में कैसे रिप्रेजेंट करें? हमें मैथमेटिकली उसको रिप्रेजेंट करना है, तो वेक्टर में क्या
सपोज
होगा?
मैम एक्स
हाउ
एक्सिस अगर
मेनी?
हम क्रिकेट को दे दें, वाई
हाँ,
एक्सिस हॉकी को दे दें और जेड एक्सिस टेनिस को दे दें, तो
हाँ,
जो वेक्टर 1 होगा, आर्टिकल 1 होगा, वो एक्स की डायरेक्शन में ही होगा, आर्टिकल 2 जो होगा वो वाई डायरेक्शन में ही होगा, और
हाँ,
आर्टिकल 3 जो होगा वो टेनिस और हॉकी के बीच का जो स्पेस है उसके बीच में लाई कर रहा होगा, उनकी डायरेक्शन में।
right, right. So if we represent that graphically in the vector space, so it is going to depict like this, right? So now when we have to write that, how we are going to write that? So let us store this information in the form of the, you can say, let us say the first column vector that represents the document 1. So in the, so here you were talking about the, when we are talking about the representation, you can have document term matrix also, you can have term document matrix also. So here I have taken in this example term document matrix. That means terms are in the rows and documents are in the columns, right? So you can take the reverse also for doing any kind of task. So here I have taken the term document vector representation. So where the one document is one column. So in this one column, let us say when we describe, so here is the first entry of the vector. This is 1. It represents, it is, sorry, it is related to the cricket. And the second one, it is related to the hockey. And 1 minute. So where the first entry is 1, that means it is more, you can say it is 100% talking about the cricket, and other 2 terms are 0. That means they are not there at all, right? And the second case, if we take up the hockey and the third to the tennis, so that means the third document, let us say it is going to be represented using 0.7.3. So that means we are depicting the value between the 0 and 1. 0 means this particular term is not there at all in that particular document, and this ratio, as we have seen, the 70% and 30% in the third column vector. So in the third document we have 70% of the you can say hockey, and 30% of the tennis. So this is how we are representing the data. So this is the complete, you can say, we have understood how we are representing the data when we have three documents. Here it is a matrix, and the data is represented in the form of matrix A, which depicts the number of terms that we have in the rows, and the columns, they are representing the documents. So here we see, if we have to understand this information, document D1 is having 100% of cricket, but hockey is not there. The term tennis is not at all there. In document 2, hockey is there, but other two terms are not there. In document 3, the hockey and tennis are in the ratio of 70:30. In document 4, the ratio of cricket, hockey, and tennis is 20:40:40. So that means the number of keywords which are available in that is, we have just represented that with the percentage of that over here, and we have represented this information. We call this matrix as the term document matrix in the vector space model. So now when we talk about, so this is, you can say, matrix A is a 3 by 7 matrix. And if we had, see, this is a small data set just for the sake of understanding. But in reality, when we talk about the documents in the real world, these documents may be your articles, news articles. It may be some articles from your magazines. It may be the web pages also. We call these web pages also as the documents. So when we have to do any kind of clustering, or we have to go for the classification, so we have to develop this term document matrix. So if we say we have 20 keywords and we have 1000 documents, then the matrix will be represented as 20 by 1000. So in reality, in one web page or in one document, 20 keywords are not enough. We have thousands of keywords, and we have, billions of documents. So you can understand this data that we have when we are talking about these web documents or articles. So this is a high dimensional big data problem. So when we have to deal with higher number of dimensions, we have 1000 dimensions, we have 10,000 dimensions. These dimensions are nothing but the keywords of that particular document. So in that case, for handling such kind of problems, what we have to do is, so because these are the large number of dimensions, all keywords may not be equally important. So in that case, what do? First step we take up is we take out the important keywords, and that we can do by, you can say, one of the algorithms, that is the principal component analysis, that can be used for, you can say, projecting the higher dimensional data into the lower dimension data, and we can find out, say, principal component analysis. This algorithm asks you how many keywords, how many terms you want, how many dimensions. So you can decide beforehand that how many dimensions you want. If out of 20 you want 10 dimensions, it will give you the 10 important dimensions, which are called as the components in this algorithm. So when you are able to see, let us say, if for 20 by 1000 matrix, you have to do the 20 by, you can say, 20,000 computations. In that case, for the, when we are able to reduce the number of dimensions from 20 to 10, our computations are also reduced to 10,000. So these, each and every computation, it matters a lot. So we have to reduce the computational complexity of the algorithms that we are working upon. Now, when we have to project this, so as I told you, this is known as the term by document matrix, because rows correspond to terms in the database and columns correspond to the documents. Now, since there are only 3 terms, let us visualize this. We can plot each column vector in the matrix A in the 3-dimensional space. Now, when we have to plot this, let us say, this kind of a plot, or the representation, if like one of you were talking about, how we can represent, just let us see the animated version of this, how we can represent this. Yeah. I missed out its link. So when we have to see, I'll try to see the other one also. So we can see the 3D version of this, that how these vectors are represented and how they are related to each other. Now, when we see these vectors, these vectors are nothing but the documents which are represented in this particular space. So all the 7 documents, how closely related to each other, and or how far apart they are from each other. this information where we can use, or this is used by the search engines when you specify one query. Let us say you give a query related to the sports in the Google search engine, then how it is going to find out the documents which are more closer to that particular query in the real world. So now let us see, uh, let us say you have given a query. So your query has, see, you can say this is this query represent that you have given a query for the tennis. So now you just want only the documents which are related to the tennis, or which are having the terms which are related to the tennis. So in that case, how this query is represented? So mathematically it is represented in the form of vectors like this. And when we have to solve this particular problem, now how do we find out which documents are represented, which of these 7 documents are closest to this particular query vector? So can you guess how do we find it out? So the
Ma'am,
best
angle
way,
between vectors.
so which will be the better one, whether this representation of graphical representation and see the angle, see how the length, or you can say when we just plot without looking at the angles, that will give us good information, or giving the angles, computing the angles will give us good information.
Ma'am, I think using angles will give us better information.
Okay, why?
मैम बिकॉज एंगल से हमें ये पता चलेगा कि उसके जो क्लोजेस्ट क्वेरी है लाइक वो कौन सी है, क्योंकि यहाँ पे हम लेंथ तो रिप्रेजेंट नहीं कर रहे हैं, इनमें हम सिर्फ पॉइंट्स रिप्रेजेंट कर रहे हैं।
हम्म।
एंड अगर जैसे क्वेरी हमारी टेनिस के लिए थी 001, अगर हम प्लॉट करेंगे
हाँ
सो दैट विल बी 001 विल बी जेड एक्सिस।
हाँ,
सो
जैसे ये ग्रीन ग्रीन एक्सिस इज क्वेरी,
हाँ ग्रीन
दिस
एक्सिस
क्वेरी,
वाली
हाँ
क्वेरी।
दिस, हाँ हियर वी आर रिप्रेजेंटिंग, राइट।
मैम ये क्वेरी होगी, और तो हम हर लाइन से इसका एंगल पता कर सकते हैं, और जो लाइन का एंगल सबसे कम आएगा मींस मैम दैट इज क्लोजेस्ट टू द क्वेरी।
Right. So this is how, see, this is the, you can, where now you understand in any of the real world application, when we are looking for the similar kind of objects, whether it is the similar kind of images or it is the similar kind of documents. So we are computing the dot product and the cosine angle between them, right? So this is how the mathematics, the linear algebra we are going to use in order to find out the documents which are closest to the query, right? So this is how the search engines they work. Let us see, now you have answered this. So the information that is contained in a multi-dimensional vector, that can be summarized as 2 dimensions measures. We have, one is the length and another is the angle with respect to the fixed directions. So the length of the vector is the distance from the tail to the head of the vector that you see over here. So if you see the distance of this vector from the tail to the head of this particular vector, and the angle between two vectors, this is the basically the measure of the angle between these two vectors in the plane. And this angle, this helps us in finding out the similarity of the documents between the query and the documents that we already have. So in order to do this particular task, again what we are doing is we are computing the cosine similarity, we can say the cosine angle between these two vectors. So this cosine angle, we know these are the two non-zero vectors, x transpose of t, transpose of x into y is equivalent to the dot product of these two vectors. And then we are taking the denominator as the, you can say, the norms of these two vectors. So computing this, we are able to find out which of these two vectors, which of these two documents, or you can say which of the 7 documents is more closer to the query document as compared to the others. So let us say we have computed, see here I have already computed the angle between all the documents with respect to the query 1 that we had. And we here see, when we compute the angles, on the basis of this information, we say document 4 is more closely related to the query document as compared to the all other documents. So, and when we compare this with the, you can say the geometrical representation, here we say from this particular graph, we were not able to derive any kind of information. So this, you can say the length of the vectors, they are not giving information, or But when we compute the angle, we are able to get the precise information that document 4 is more closer to the, you can say, the query document as compared to the others. Now, let us say you have another query. So, compute the angle between these for this query with respect to all the documents. You note down this query. I will show you the all the information about that, the documents that we had. I will show you the term document matrix. Have you note down this? Yes. Yes, please.
Yes, ma'am.
Yes.
Okay, I'll show you the other information that we were talking. Yes. Now this again we have this document matrix. Now you compute the angle between all these documents and then tell me which document is more closer to this particular query. So this is how your vector space model that works in the real world for the various search engines. So finding out the similar kind of documents. So you can do it, you can apply this vector space model everywhere whenever you have some classification problem and you want to classify which to which particular class your new document will belong to on the basis of this information. You can find out the cluster to which a particular document will belong to on the basis of this particular information. And also for the recommendations, like if you have to give the recommendations for the movie, so again there also we are trying to find out the, you can say movie is one document. On the basis of certain information we can create a matrix and we can find out the similarity of one movie with the all the other movies, and you can recommend the similar kind of information, like if you have information about the movies, like who are the directors, producers, the the actors, then the genre, so much of information is available about them. So on the basis of you can say this is your cosine similarity that we are computing, that is also called as the projection of orthogonal projection, or the angle between the vectors, which is used to find out the similarity between the documents.
मैम सो इस पर्टिकुलर एग्जांपल के लिए लेंथ इंपॉर्टेंट नहीं है.
नहीं, this is what we are trying to tell, that when we have to find out the similarity, see if we say the length of the document, लेंथ ऑफ द डॉक्यूमेंट इज नॉट इम्पोर्टेंट, उसमें हो सकता है कुछ और कीवर्ड्स हो, टर्म्स हो जिनका कोई यूसेज ही नहीं है, बट द इम्पोर्टेंट कीवर्ड्स आर मोर इम्पोर्टेंट ना.
ओके मैम.
Like हम देखते हैं कि see if you have worked upon what do we do when we are working with such kind of see the various pre-processing tasks, we remove the stop words, all the articles, is, am, are, the kind of things. After that we find out the important terms and we call them, the only the important terms are called as the keywords, not all the terms are called as keywords.